isotopes. Copper 63, which has an actual mass of 62.93 grams per mole, and copper 65, which has an actual mass of 64.93 grams per mole. In any sample of copper atoms, 69.1% will be copper 63, and 30.9% will be copper 65. Calculate the average molar mass of naturally occurring copper. So let's see. And just let me write down a couple details here. So 62.93, 69.1%, 64.93, 30.9%. All right. So I'll stop sharing. There we go. And this is homework 02-03. And this is for copper 63 and copper 65. We have the molar mass and the percent natural abundance. Now, and sorry, I love my units. I see these numbers here without grams per mole and I get nervous. So a couple things about this. So first off, copper 63 is one of the isotopes. Copper 65 is another. If the question is, why is there not copper 64? The answer is well beyond the scope of this class, and that's okay. When we're presented with isotopes in this course, we accept that they exist. And I can say more about that, but these are the two isotopes that are naturally occurring. And so if you were to take a copper pipe, the copper atoms in that copper pipe would be 69.1% copper 63 and 30.9% copper 65. And these numbers, again, are given to us. And the only thing we have to know how to do is take these percentages and the masses and find the average molar mass. And the average molar mass equation is on your conversion and equation sheets. And so let me bring those up right now. Those are available under your syllabus and schedule menu, and they have a whole bunch of good information on them. But this one says, well, it should say average molar mass is going to be the mass of the first isotope times its percent, plus the mass of the second isotope times its percent, plus the mass of the third isotope times its percent, because sometimes there are 3 isotopes, and sometimes there are even 4 isotopes. But for this one, there's only 2, and so we're going to end this equation with 2 isotopes. And the equation will be like this. Take the mass of the first isotope, times its percent, plus the mass of the second isotope times its percent. And of course, you notice that the percents add up to 100%, as always. And then divide by 100%. And for this one, your work definitely counts. I do need to see this work. When we multiply this out, (62.93) times 69.1, 69.1 plus 64.93 times 30.9 divided by 100 equals 63.55 to 4 sig figs. And 63.55, this is the average molar mass. And what I've suggested and told you, in fact, in the past, is that the numbers on the periodic table are the average molar masses for each element. And so the answer for this is not in doubt. The answer is we know that the average molar mass for copper is 63.55. The point of doing this question is that you show the process of how you get those numbers in terms of the isotopes that occur naturally. So if I were to ask you about the process, or if this was to be a recitation question that you had to work and you had to describe this process, you would talk about how these are the only two isotopes that occur in these percentages with these masses, and all those numbers have to be given to you. And then you would say that the average molar mass is going to be mass times percent plus mass times percent, and that this is called a weighted average, weighted by the percent that the each type of atom exists in nature, and that this number must be the number on the periodic table, because the periodic table has the average molar mass values for each of the elements. So, and that should be our answer for this. Are there any questions about any of the work that I've done?
I have a question.
Please, go ahead.
So when you multiply the grams per mole times the percent, do you actually find 69.1% of 62.93? Or you just pretend like the percent isn't there?
So when I do this on my calculator, I do not hit the percent button, if that's your question.
Okay. So you should pretend as if it's a whole number?
I use it as a whole number and think of this as a unit. The other way to do this, by the way, is, and I'll do this in a different color, my favorite color, green. If you take away the denominator and you treat each of these as fractions, so this would be 0.691, and this would be 0.309. So you've basically said, instead of percents, I'm going to use fractions of the whole. And so that's the other way of doing it. And you can see that this 0.691 is 69.1 divided by 100. So it's just like I've factored it out in some ways too. But these are the fractions. And it's also, sometimes you'll see it called fractional abundance. And it is true that the fraction that something exists as is always the percent divided by 100. Right? Because percent means per 100. And anyway, just thinking of other ways to do this that still get the same answer and might help you understand it. Any other questions about this? Okay.